Hello everyone, let's take a look at our next problem. Let T map V to V be a linear transformation where V is finite dimensional. Show that exactly one of the following properties holds. First property is that T of V is equal to 0 for some V not equal to 0. And the second property is that T of X equals V has a solution X for every vector V. Okay. So this is, standard result when you're looking at systems of linear equations. How do we prove it? I don't want to use like a matrix. I don't in any way want to refer to matrix representations of things. So, wait, is this even true? Like, I don't like, as it's worded, I don't like exactly how this is, as it's worded, this isn't exactly true unless this condition requires the solution to be unique. Right? Like, I might have a linear transformation, T of X is equal to V, may have many solutions. And if it has multiple solutions, let's say x1 and x2, and then T of x1 minus x2 is equal to 0. So these can both be true if this solution is not unique. So it really should say has a unique solution. I mean, the text I'm reading does say has a solution, but in the typical math phrasing of things, this would mean this doesn't rule out non-uniqueness. Anyway, well, I'm going to start by assuming 2 is true and show that 1 cannot be true. T of X equals V has a unique solution. I'll call it G of V. So this says that T of G of V is equal to V. Now, and so G itself will be a linear transformation. I'm not going to prove that, but it's verifying the properties of a linear transformation for this function g would not be difficult. In fact, let me just go through it. Okay, so I've proven that g is a linear transformation. G of 0 must be equal to 0. G of AV must be equal to A, G of V. All of these are just using the fact that that this equation always has a unique solution. Okay, so let's go back to what I want to do here. This says that if T of V is equal to 0, then V is equal to G of 0, which is equal to 0, which is the same, which says that property I cannot be true. So I have property 2 implies the negation. Property 2 implies the negation of property 1, which is what I wanted. So now I want to show that 1 implies the opposite of 2, and that should be easy, right? Let V be in our vector space such that T of V is equal to 0 and V is not equal to 0. Okay. So then either Tx equals W has a solution, or no solutions. Okay, so if it has no solutions, then property 2 is false. If it has at least one solution, well then Tx plus V is also equal to W, because T of V is equal to 0. Because V is non-zero, x plus V is not equal to x, so this says that solution is not unique. So this says that statement 1 implies the negation of statement 2, and we're done. Okay, so we've shown that only one of these two statements can be true, because if I assume one of the statements is true, I can prove that the other one is false. You can probably do this first one. Probably do that faster. Now, like this function g, this linear transformation g, is of course going to be T inverse, as we all know it. I didn't really exactly require that. I really only needed it to be, I guess this is what, like a right inverse. Yeah, I guess proving that g itself was a linear transformation, was it completely necessary? Actually, I don't think so. No, not at all. Right? If we're assuming property 2 is that Tx equals V has a unique solution. But if the right-hand side is 0, then the vector 0 is always a solution to that. And if we're assuming it's unique, then it is the only solution. So there can't be a non-zero. Yeah, I really went a long way about this. I guess if I'd slowed down and put a little bit more thought into my approach, or exactly what we were being asked to do, then this might have been a little shorter. I still don't like the wording of the question, right? Tx equals V has a solution x in V for every V in V. But really should say has a unique solution, because reading it as understood, reading it typically you wouldn't assume uniqueness. Anyway, pretty long roundabout way of doing this, way more time than it should have taken, but overall we got there. If I have any more to say about it, I'll put it down in the description. Thanks for watching. All right, so after editing what I'd recorded earlier, I realized I made a pretty significant mistake in what I was doing, much basically related to my understanding of the question and the whole setting and what's going on. So the two statements that were given here are t of v is equal to 0 for some v not equal to 0 in the vector space V, and the other one being t of x equals v has a solution x for all vectors v in the vector space V. I focused a lot on these statements, but what I didn't do is I didn't really focus on the initial assumptions about the transformation t. So t maps v to itself, and the dimension of v is specified to be finite. When you have this in mind, you don't actually need to specify that this equation has a unique solution. That'll kind of be if there's always a solution to this equation and t is mapping v to itself with a finite dimension, then that will in fact imply that the solution is unique. So as I was going through my mind and saying that these two statements, for them to be mutually exclusive, we would have to specify that the solution is unique. You don't need to specify that as part of the assumption. And in fact, the main way that I think proving this thing should be done is by analyzing the dimension of the kernel and range of the map T. So I'm basically going to redo this problem, but I'm going to do it correctly. So the main thing to realize here is that the dimension of V is equal to the dimension of the kernel of T plus the dimension of the image of T. Kernel of T is sometimes called the null space of T. It's the set of all vectors that T maps to the 0 vector. And the image of T is, of course, the collection of all vectors in V such that this has a solution. Okay. Now, let's suppose that the dimension of V is equal to n. Okay. Well, if this statement is true, then this is saying that, so if this always has a solution, then the image of T is exactly V. And so the dimension of the image is n. And that says, when we look at this then, it means that the dimension of the kernel has to be 0. And that contradicts this statement. So if statement 2 is true, then statement 1 is false. And let's do the opposite. If statement 1 is true, then this says that the dimension of the kernel is at least 1, but then the dimension of the image has to be strictly less than n. And if the dimension of the image is strictly less than n, well then that means there is some subspace of V which is not in the image of T, and so statement number 2 is going to be false. So kind of like I proved in the first part of this problem, at least, so 1 implies the negation of 2, and 2 implies the negation of 1. So these statements can't both be true. To see that at least one of them must be true, well, the dimension of, these two things have to sum up to n. So either this is 0 or it's not. If this is 0, then statement 2 is true. If this is non-zero, then statement 1 is true, and we're done. The only thing that actually is left to do here is to prove that this equation holds, so that the dimension of v is equal to the dimension of the kernel plus the dimension of the image. I'm going to prove that in a slightly more general setting. So the way I'm going to do this is I'm going to assume that T maps v to w, so it doesn't necessarily have to map a vector space to itself. But then we still have that the dimension of v, or at least we want to prove that the dimension of v is equal to the dimension of the kernel of T plus the dimension of the image of T. So here's how we're going to do that. We're going to let v1 up to vk be a basis for kernel of T, and we're going to let w1 up to wm be a basis for the image of T. Okay, so in particular, this means that there are vectors, let's call it v prime 1, or let's call it u. Let's use u. u1 up to um such that t of ui is equal to wi. Okay, and that's because this is a basis for the image of T. So in particular, each of these vectors is in the image of T, meaning that there is a vector in V such that T of u is equal to W for each of these W's. Okay, so what I want to show now is I claim that the collection V1 up to Vk and U1 up to Um is a basis for V. Okay, this will imply that the dimension of V is equal to k plus m, but k is the dimension of the kernel and m is the dimension of the image. And so if I can show that this is a basis for V, then I've shown that this equation holds, and the entire question will be done. So how do we want to do this? We need to verify two things here. The first is we need to verify that the span of these vectors is equal to V. Okay, so the way I'll do this is I'll let V be any vector in V, arbitrary. Okay. What do I want to do now? How do I show? So I need to show that this V can be, I need to show that V can be written as a linear combination of VI's and UI's. So I think the way to do this is we'll define W to be equal to T of V. Now W is going to be, W is in the image of T.
So W is equal to A1 W1 plus up to AM WM, right? W is in the image of T, and so it can be written as a linear combination of these. Does this tell us anything? Does this help? Maybe then what I can do is consider V minus A1U1 plus up to AMUM, where these U's are the basis W pulled back like that. Okay, if I take T of this, T of V minus this thing, okay, so this is equal to T of V minus, well, W really, right? Which is equal to 0, right? If I distribute T through here, T of this is equal to W, and W is equal to T of V, so that equals 0. So this says that V minus, this says that this vector we're considering here is in the kernel of T. And that says, because it's in the kernel of T, this means that it can be written as a linear combination of the basis vectors of the kernel, right? If this is in the kernel, then it can be written as a linear combination of the kernel basis. But if I now just rearrange this, I have V is equal to B1 V1 up to BK VK plus A1 U1 up to AM UM. And I have V now written as a linear combination of the vectors that I'm trying to show form the span of V. And so I'm done. Okay, I have now in fact shown that the span of these vectors is equal to V. The next thing I need to show is that this collection of vectors is linearly independent. Okay, so I need to show it's linearly independent. We're going to consider something similar, the sum of A1 V1 up to AK VK plus B1 U1 up to BM UM. Suppose that equals 0. I'm going to take T of both sides. It says T of this whole thing is also equal to 0. But these vectors are all in the kernel of T. And so when I distribute T through this, all the T of V1 up to T of VK are equal to 0. So this can be written as B1 T of U1 plus ... BM T of UM is equal to 0. But these TUs, this is what we were calling W, right? B1 W1 plus up to BM WM is equal to 0. But the W's, W1 up to WM, we said is a basis of the image. In particular, W1 up to WM are linearly independent. So this tells us that BI is equal to 0 for all I, right? If I have a linear combination of W's that adds to 0, that linear combination must be the 0 combination. And so now I can substitute, we know that these all have to be equal to 0, but now we know also that the sum of A1 V1 up to AK VK is equal to 0. But now, well, the V's are also assumed to be linearly independent because the V's are a basis of the kernel. And so once again, I have that AI is equal to 0 for all I. So I have that my collection v1 up to vk and u1 up to um is linearly independent, and the two statements together show that this is a basis for v. And that immediately means that the dimension of v is equal to k plus m, but k is the dimension of the kernel of t, and m is the dimension of the image of t. Okay, so we know that that equation up there holds. We've proven this, okay, and that's the only equation we actually needed to prove our original idea that these two statements are mutually exclusive. Only one of them can be true, and that at least one of them must be true, which is what the question was asking for originally. Yeah, so I had a big misunderstanding of what was going on when I first tried to solve this problem, which was a couple days ago. And after I'd fully edited everything and gotten it ready to go, I realized what my mistake was. So I'll go back and put in some text bubbles to say that almost everything I'm doing there is either unnecessary or in fact kind of incorrect. But this is I'm pretty sure the way that this problem was intended to be solved. If I have any more comments on this one, I'll put them down in the description. Otherwise, thanks for watching.